Hello, everyone, and welcome to today's webinar. We're excited to kick off C2 Smart's State of the Field series focused on connected vehicles and their deployment. This is the first of 4 planned online events addressing connected vehicles and research around connected vehicles, which will be delivered over the next month, and will be concluded by a roundtable session featuring leading policymakers and research on the future of connected vehicle implementations. So for those of you who have not been with us before, C2 Smart is a US DOT Tier 1 transportation center conducting research and education on advanced transportation and mobility topics and solutions. So for a quick programming note, today's webinar will feature a presentation followed by interactive Q&A. So please enter your questions into the Q&A box by clicking the button on the bottom of your screen. Also note that this meeting will be recorded and available on C2 Smart's YouTube channel after this event concludes. So with that, today we are very excited to be joined by Professor D. Yang of Morgan State University to talk about his work as part of the NYU team at C2 Smart, working as part of the US DOT Connected Vehicle Pilot Project in New York City, led by New York City DOT. D is an assistant professor at Morgan State University and a recent graduate of the PhD program in transportation engineering at New York University, advised by Professor Khan Osbey. I had the pleasure of knowing D over the last few years and the great work he's done as a student at C2 Smart, and really look forward to today's talk. So with that, I'm going to hand it over to D to begin your presentation.
Thank you, Shuri, for the introduction. So can you see my screen and hear me well?
Great.
Okay, great. All right, so let me just adjust the Zoom real quick. Okay. So hi, everyone. Thank you for the introduction, Shuri, and good afternoon, everyone. My name is Di Yang. I'm currently an assistant professor at the Department of Transportation and Urban Infrastructure Studies at Morgan State University. Like Shuri mentioned, I'm a recent NYU C2 Smart alum, and it is my great honor to be invited back by my alma mater today to kick off this great series of webinars that are related to the New York City Connected Vehicle Pilot Deployment Projects. So my topic today is improving safety through connected vehicle technology, New York City Connected Vehicle Pilot System Performance. So because this is the first webinar of this series, so before we get into the nitty-gritty about the data, methodology, and findings, so I would like to spend a little bit more time at the beginning to introduce a little bit about this project. Okay, so the sponsors of this project include the United States Department of Transportation and the New York City Department of Transportation. And there are several stakeholders involved in this project, including the New York City Citywide Administrative Services, New York City Information Technology and Telecommunications, Metropolitan Transportation Authority, Trucking Association of New York, PASS Coalition, TransCore, University Transportation Research Center, Onboard Security, KLD, Cambridge Systematics, Anheuser-Busch, and Together for Safer Roads, New York University, as well as the C2 Smart University Transportation Center at New York University. So if you would like to know more about the sponsors and stakeholders, please feel free to visit the website right here, which includes more information about the sponsor stakeholders, as well as other related information about the New York City Connected Vehicle Pilots. So here is a little bit of a history about this project. So basically, this project includes 3 phases lasting for more than 6 years, from September 2015 to December 2021. So the first phase is concept development. So basically, in this phase, it lasts 12 months. Basically the team together lay out the goals, the deployment strategies, and so on. And in the second phase is the design, deploy, and test phase, which lasts for about 52 months. And then the final phase, phase 3, is the operate and maintain phase, which lasts for the entire year last year. So in the third phase, the operate and maintain phase, one of the key goals of this phase is to conduct safety performance evaluation. So please allow me to introduce the core safety performance evaluation team, which includes Dr. Mohammed Talas, who is at the New York City Department of Transportation, and is also the project manager of this project. And also David Benavelli, who is at TransCore and is the system engineering lead of this project. Bob Rausch, who is also at TransCore and is the system deployment lead of this project. And we have Kier OP, who is at Cambridge Systematics and is the performance measurement lead of this project, as well as Dr. Kain Ausbay at New York University, Department of Civil and Urban Engineering, and is also director of the C2 Smart University Transportation Center. So within the safety performance evaluation team at the NYU side, these are all the people that have been working on the safety performance evaluation for the NYC CV PT project. Dr. Kain Ausbay, who was my PhD advisor when I was at NYU, and also my colleagues, Dr. Jingqing Gao, who is a senior research associate at C2 Smart Center, and Mr. Fan Zuo and Mr. Disha, who are currently PhD candidates at NYU. And please allow me to thank again the United States Department of Transportation, New York City Department of Transportation, Cambridge Systematics, and GHK Transport for their constant support throughout the entirety of the project. So basically, the work I'm going to present today is a joint work of all of the sponsors and the people that I mentioned. So basically, I'm very lucky to be able to present this work, but this is a joint work from all of us. And in terms of the reports, as of today, several reports have been published regarding the NYC CV PD projects. So the first one is the NYC CV PD Phase 3 System Performance Report. So today's talk will largely be based on the report, from this first report. And besides that, there are several other reports, including the Mobile Accessible Pedestrian Signal System, or PATSIC application, test summary and evaluation report. So this report is largely focused on a specifically designed application that focuses on pedestrians, so to navigate pedestrians safely throughout the cities. And there will be a dedicated webinar for that later on in this webinar series. And the last report is Understanding and Enabling Cooperative Driving for Advanced Connected Vehicles in New York City. So this report is dedicated for cooperative driving with using connected vehicle technologies, for use cases in New York City, basically. And again, today's talk will be based on the first reports. And because due to the time limitation, I cannot talk about all the details regarding the data collection, processing, methodology, and the findings. If you're interested to know more about what I talk about today, please feel free to check out the first report as well as some other reports to know more about the performance evaluation aspect of the NYC CV PD project. Okay, so now let's look at the content of today's presentation. So today we will first go over the project overview and then discuss the experimental design of this project, followed by the data collection, processing, methodology, performance evaluation results and findings. And then we're going to conclude today's presentation with conclusions and lessons learned. So, for those of you who are not familiar with the connected vehicle pilot sites, there are actually 3 connected vehicle pilot sites funded by the US Department of Transportation, which includes the Wyoming pilot sites supported by Wyoming Department of Transportation, New York City pilot site supported by the New York City DOT, as well as the Tampa connected vehicle pilot, which is supported by the Tampa-Hillsborough Expressway Authority. So, each of these CV test sites, they all have their specific goals. There may be some similar goals, but each of these sites, they have very unique and specific goals that they want to achieve. And in terms of New York, there are basically 2 goals. The primary goal is to improve safety through the reduction of vehicle and pedestrian crashes, injury, and fatality. And the secondary goal is to improve mobility and reliability through crash prevention and lower crash severity. So basically, just by looking at these 2 goals, we can see that improving safety and reduce vehicle crashes is actually one of the main fundamental goals of the NYC CV project. In today's webinar, I will go over the findings that we found during the performance evaluation phase regarding the potential safety improvements of the connected vehicle technologies. And in terms of the infrastructure of the NYC CV pilot, so first of all, 3 distinct areas in the boroughs of Manhattan and Brooklyn were installed with the roadside unit, or RSUs. So as you can see in the picture on the right, we have some areas in the midtown of Manhattan and also a large corridor in downtown Brooklyn. So with the installation of these RICUs, vehicle to infrastructure or V2I applications can be enabled in this equipped areas. And also for V2V applications, our vehicle to vehicle applications, they can be enabled anywhere in the city that the CVs came into close contact with each other. Because for V2V applications, they do not necessarily require the input from infrastructures. And more specifically, 470 RICUs has been installed throughout the entirety of this project. And approximately 3,000 vehicles are equipped with the aftermarket safety devices, or AISDs. Are basically these 3,000 vehicles. They are the connected vehicle fleet of these entire projects. And in terms of applications, we have a total of 13 safety applications and 8 operations applications. So today I'm gonna show some of the results from these 13 safety applications. And if you're interested to know more about the results for the operations applications, you may look at the first report that I mentioned that includes all the findings for both operation and safety applications. And in terms of safety applications, for V2I applications, we have the following applications, including red light violation warning, speed compliance, curve speed compliance at work zone, oversized vehicle compliance, or specifically we focus on over height of the truck, and also emergency communications, evacuation information. And for the V2V applications, again, they can be enabled anywhere around the city. They have the V2V applications include forward collision warning, emergency electric brake light, blind spot warning, lane change warning, intersection movement assist, and vehicle turning right in front of bus warning. So besides the V2I and V2V applications, there is a third type which focuses on the pedestrian applications that includes the pedestrian in signalized intersection warning to vehicles, and also the mobile ped signal system, which were designed specifically to assist vision disability pedestrian navigation. So again, like I mentioned, there will be a dedicated webinar specifically to talk about all the pedestrian applications. So please stay tuned. And also, as you can see on this slide, 3 of the V2I and V2V applications are colored in gray. So this indicates that after completing the data collection, there are not enough data, or the sample size for the warning event for these 3 applications, they are very low. So, I mean, in today's talk, we will not talk about the safety effect of these 3, and we will go over the findings and the data collection and all that for the other safety applications, basically. And before we move forward, let's quickly look at a specific example. Here, I will show you a video about a speed compliance application. So this is taken from the webinar on July 20th, 2021. That's called Operational Capacity Showcase webinar. So the slides and the presentation and also the recording of this webinar is open to the public online. So feel free to check out more demonstration videos about other safety applications in the CV project. Okay, so now let's look at this video together. So pay attention to the speed indicator here. So basically, after the speed is over 25 miles per hour, you will hear several beeps, and also followed by a human sound reduced speed, right? So this is just a quick demonstration about one of the safety applications in the field. Okay, and in terms of the experimental design, so in this project, before-after treatment control group design has been implemented. So this is a quick illustration about this experimental design. So basically, all the CV fleets have been divided into either a control group or a treatment group. And the entire study period from January 1st, 2021 to December 31st, 2021 are divided into 2 periods, the before periods and the after periods. So basically the before period is from January 1st to May 19th, and the after period is from June 1st to December the 31st. And there's a small period in between. So that is the transition period. Basically, during that time, connected vehicles in the treatment group will be, will be transitioning to, receiving active CV alert, right? So basically, in the before period, all those connected vehicles will not receive any warnings. But in the after period, connected vehicles in the treatment group will receive active warnings. And as soon as the warnings have been turned on for those connected vehicles in the treatment group, they will not be silenced, right? So that basically we're gonna ensure the drivers will hear these warnings throughout the entirety of the after period. And also there are approximately 7% of the entire connected vehicle fleet have been assigned to the control group. And if you'd like to know more about the experimental design, as well as different vehicle makes and different vehicle types, please feel free to check out this report right here, which is also the first report that I mentioned in the beginning. And in terms of the data collection and obfuscation, so basically in this project, the basic safety messages, or BSMs, are transmitted immediately before and after warnings were collected. So basically for each safety applications, the number of seconds recorded before the warnings and after warnings vary. But generally speaking, we have at least like 5 to 10 seconds before the warning and 5 to 10 seconds after or more after the warning, so that we know what is going on immediately before and after the warnings are issued. And the data collected from these New York City connected vehicle projects are open to the public on the US DOT's ITS Data Hub CV Pilot Data Sandbox. So feel free to check it out if you're interested. And besides collecting the data, the NYC CV PD project actually implemented a data obfuscation procedure, so that basically the aim for that is to protect the privacy and the liability issues about the participants. So more specifically, the detailed latitude and longitude coordinates of the BSM data, they are replaced with an artificial Cartesian coordinates. So, and also the location bins. And the unique IDs of the vehicles are also removed, and the date and time, they are replaced with time bins, right? But also we do not know the exact date and time of a specific event. So, I mean, on the right, here's an illustration about the data obfuscation, basically the results after the data obfuscation procedure. As you can see, the 0 point in this artificial Cartesian coordinate system represents the location where the warning is issued, okay? And as you can see, for this application, 7 seconds before the warning and 9 seconds or 10 seconds approximately after the warnings that the data have been recorded. And also the 0 second means that the warning is issued right here. Okay, and then as you can see, the trajectories of all the participating connected vehicles are recorded, and we know the relative relationship between them. But what we do not know is the exact location and time. And what we know is that, for example, if this event occurred in 2021 March on a Tuesday and in the afternoon, and we know that this event occurred in New York, Queens, and also on a freeway. Right, so this is a brief introduction about the data collection and also the obfuscation procedure of this project. So if you'd like to know more about the data collection and obfuscation, please feel free to check out these two reports right here. So the first one is a report from phase 1, which lay out the procedure of the obfuscation, and the report from phase 3 include more supplemental details about that. And after collecting the data from the field, we employed a very detailed data cleaning and processing procedure to make sure that the data that we use to get the results have been cleaned, as much as possible. So basically, this is the very detailed procedure that we employed, which is taken directly from this phase 3 report. So generally speaking, what we did is that we identified several potentially illogical events or illogical observations from the field BSM data, which includes the illogical events warning time scales, irreasonably high, zero, or constant speed, large elevation between host and target vehicles, stationary vehicles, illogical trajectories, including large gaps in the trajectories, and also if the relationships among host and target vehicles are illogical, and detailed vehicle trajectory speeding claim, right? So we identify the potential, illogical or erroneous speed observations from the field. So after identifying all these potential situations, we first try to clean and repair some of these events as much as possible. So and then if it is not possible to clean and repair, we will remove the events from the consideration and to ensure that the results that we obtain are basically obtained from using the data as clean as possible. Again, so for more information about the data cleaning and processing, please feel free to check out this report right here. Okay, so yeah. Right. Okay, so now let's look at the safety evaluation methodology. So basically in this project, we employed 3 branches of methodologies to ensure that we can get the safety performance evaluated of the connected vehicles from different aspects. So the first one is to use the ASD data or the BSM data collected from the field. So what we did is that we first extract safety-related driver response behavior measures from the field, observed ASD data, and then we apply the gain score method, which is a relatively commonly used method in statistics to conduct before-after analysis. And the second branch is the crash-based analysis. So here we employed the before-after safety analysis, which is a very common method in transportation safety to get the treatment effect of safety-related countermeasures. So in this project, connected vehicle project is a potential safety-related countermeasure. So we employed the basic structure and framework about the before-after safety analysis in transportation safety for crash-based analysis. And we employed a survival analysis approach to conduct this analysis. I will talk more about that later on. And the third branch is simulation-based surrogate safety measure analysis. So basically, from the first 2 branches, we use data collected from the field. And the third branch, we use the microscopic simulation to conduct a safety evaluation. And specifically, we calibrate the simulation model for both safety and operational measures and incorporate driver behavior models. And basically, we employ the multi-objective stochastic optimization method to do that. And I will also talk more about each of these branches later. Here, let's look at the first branch, which is use the ASD data. So here we extracted, 3 safety-related driver response behavior models by, going through past studies in the literature. So the first one is the deceleration difference. It is defined as the difference between maximum deceleration after a warning is given and the deceleration when the at the time when the warning is given. So basically, the main goal of this measure is to assess the driver's tendency to slow down, or basically the degree, the driver's response degree. And the second measure is time duration to slow down to speed limit after warnings, which is defined as the time duration between the time when a warning is issued to the first time the observed speed is below the corresponding speed limit. Right, so we want to see how long does it take for drivers to react to basically slow down to speed limit. And this measure is mainly designed for all the CV applications that are correspondent to to reduce speeding events. And the third measure is time duration to first deceleration after warning. So basically, this is a more generalized measure compared to the second one, and is applied to be used for all the CV applications that do not necessarily have a speed limit. And it is defined as the time duration between the time when a warning is issued to the first time the driver decelerates. And the last one is a very commonly used surrogate safety measures, time to collision, which is defined as the time for 2 vehicles to collide if they continue at their present speed and on same path. And in terms of statistical analysis, we include a commonly used gain score method to analyze the before-after control treatment group design. So basically what we did is that we first calculate 2 differences. One represents the differences between the performance measures in the treatment group from the before period to the after period. And then the second difference is the difference in performance measures in the control group from the before period to the after period. And then we take the difference of these 2 differences so that we can get the safety effect, or basically the change in driver behavior based on the before-after control group design. And due to obfuscation, we aggregate the safety measures to obtain the safety performance measures, and the confidence intervals are constructed by assuming the sample distribution follows the student T distribution. And that is the first branch of the methodology. And the second branch is deal with crash data. So basically, we employed a survival analysis approach, which was proposed by, which is a joint work by Dr. Quincy at Old Dominion University, Dr. Kain Osbey, who is my advisor at NYU, and also Dr. Hong Yang at Old Dominion University, and also me, right? So basically, the main motivation for the survival analysis approach is that in real-world applications, or to assess safety countermeasures in the real world, it may not be always possible to find a proper reference group, right? So when that reference group is not feasible, I mean, what the traditional before-after safety analysis method, including the Bayesian, the empirical Bayes or the full Bayesian method, they may lose their power, right? So that is one of the main motivations to propose this survival analysis approach. Basically, we instead of model the crash frequency or crash count, which is one of the most commonly used safety performance measures for crash analysis, we look at the time intervals between two consecutive crashes. And then again, this method can relax assumption of the reference group. And this is basically very sweet for the NYC CV project, because like I mentioned, for the V2V applications, they actually can be triggered anywhere in the city, right? So in this case, in addition to the data obfuscation, it is basically impossible or very extremely difficult to find a proper reference group, for the analysis, right? So that's why we apply the survival analysis approach to analyze the crash-based safety effects for the CV project. And here is a quick illustration of this method. The red dots represents the crashes, and then we are modeling the time intervals between them. So here for crash analysis, the before period is from January 1st, 2021 to May 31st, 2021, and the after period is defined from the beginning of June to the end of September. So the reason why the end of our period is at the September but not as December is because by the time when we are doing the analysis and generating a report, this is basically all the data that have been available to us. But all the basic safety message data collected throughout the entire year, they are open to the public on the ITS Data Hub. And here is a quick description about this survival analysis method. So here we by modeling the intervals as exponential distribution and combined with the gamma error here, we can estimate the treatment effect and also the crash modification factor or CMF, which is a commonly used measure in transportation safety to measure the treatment effect. If you're interested to know more about the survival analysis approach, please feel free to check out our paper right here. And the third branch is the simulation-based method. So here, I mean, in the future, we have another webinar dedicated to this topic. So today, I'm going to briefly give you guys a little bit of preview about this third branch, but stay tuned for that webinar. So, I mean, one of the main objectives, to use simulation models to evaluate the safety effect of connected vehicles is that, we need to be able to properly analyze the safety benefits of connected vehicles, right? So in order to do that, I mean, it is not only necessary to calibrate the simulation model for traditional operational measures, including volume, travel time, and turning movement, etc. But it is also very important to calibrate the macroscopic travel simulation models for safety measures, right? So here we employed a traffic conflict severity distributions, to do that. And then we use the open source micro simulator Sumo software for our analysis. And then we integrated 7 of the connected vehicle applications and the driver behavior model into the simulation model. And then we applied a multi-objective stochastic optimization, SPSA, for the calibration. Okay, and again, if you want to know more about the simulation-based safety evaluation and also the calibration procedure, please stay tuned for that specific webinar. Okay, so now let's look at some results. So first of all, let's look at the results for the speed compliance application. So after data collection or after data processing and cleaning, total number of events for speed compliance is a little bit more than 40,000 events. And then basically compared to the silent warning scenarios, there are additional 47 events per 1,000 events that shows that drivers slow down to the speed limit when treatment was enabled. So basically we saw there are more events or more drivers try to comply with the speed compliance warnings after it has been turned on. And also in terms of driver response behavior, we saw an extra deceleration, 0.148 meter per square second extra deceleration on average after the speed compliance warnings were issued. And also there is a small reduction in time duration to slow down to speed limit. And all of these three findings, they are statistically significant according to the 0.05 significance level. So which indicates that there are some safety benefit or safety improvements after the speed compliance warnings has been turned on. I mean, again, so these results, they are based on the data collected from the fields, right? So they do not include results for the simulation. And for the simulation results, please feel free to check out the webinar dedicated for simulation. And here, let me show you a typical example about the speed compliance applications. As you can see in the picture on the left, so here at the 0 point of this coordinate system, that is the location where the speed compliance warning has been issued. And this is the direction of travel. As you can see in the pictures on the right, first one is the speed. So basically here, 0 time means that this is the time when the speed compliance warning is issued, right? As you can see, after the warnings are issued, there's a brief increase in the speed of the vehicles, but then followed by a deceleration, which can also be seen from the longitudinal acceleration of these vehicles, right? So after the warnings are given, at the time of warning are given, the drivers are accelerating, but then it slowly turns to deceleration, basically. And that is the first application. Secondly, we have the curve speed compliance. So the curve speed compliant applications is only installed at one curve that connects, the local streets to the FDR freeway. So, I mean, if you wanted to know more about that, please feel free to check out the report. So after the data cleaning and processing, there are a total of 27 events. And then we also analyzed the potential reduction in vehicle speed at the entry of the curve, as well as the lateral acceleration in the curve. We can see there is a positive reduction in vehicle speed and also a positive reduction in lateral acceleration in the curve. And they are all statistically significant according to the 0.05 significance level. And in terms of the driver response behavior, we can see there's a decrease in the deceleration difference. And this decrease is statistically significant at the 0.05 value. So basically, we are expecting to see an increase in deceleration difference. So this is actually proved by just manually looking at these 27 events. So among these 27 events, drivers do not show the deceleration behavior after warnings are issued. And for the speed compliance in work zone, after the data cleaning process, we have 2,665 events, and the driver response behavior analysis, we analyzed the deceleration difference as well as the time duration to slow down to speed limit. So for both of these driver response behavior, we can see that there are extra decelerations in the drivers after receiving the warnings, and also there are positive reduction in time duration to slow down to speed limit, and they are all statistically significant. So which means that for the speed compliance in work zone application, there are safety benefits or safety improvements after these warnings have been turned on. And then let's look at another V2I application, that is the red light violation warning. So after the data collection, we have a little bit more than 2,000 events. And when we look at the number of events, basically number of events that drivers are likely to comply to the red light violation warning. So compared to the silent warning scenarios, there are approximately 152 fewer likely red light violations per 1,000 events when treatment was enabled. Right. So basically, here to identify a potential red light violation, we look at the driver's speed. If driver did not come to a full stop after receiving a red light violation warning, then we identify as a very likely red light violation. So this is how to identify the potential red light violation using the ASD data. And in terms of the driver response behavior, we look at the deceleration and also the time duration to first deceleration after warning. So basically, we can see that there are extra decelerations after the red light violation warning has been turned on, as well as a positive reduction, even though very small, in the time duration to first deceleration after warning. And this is also just marginally insignificant at 95%, which means that the p-value estimated are a little bit, just a little bit larger than the 0.05 significance level value. So generally speaking, for the red light violation warning, we still see some benefits, in terms of, improving safety, basically to try to basically encourage the drivers to stop at the red light. And that are all the applications for V2V communications. And now let's look at the results for all the V2, I'm sorry, that is previously I talked about V2I applications. Now let's look at the results for V2V applications. So we look at 5 V2V applications, which are forward collision warning, emergency electric brake light, blind spot warning, lane change warning, and intersection movement assist. So these are the number of events after the data cleaning and processing procedure. So here, the safety performance measures, we used 15 percentile of TTC value, which is a commonly used TTC value in the field. Basically, we want to capture the extreme TTC values, extremely small TTC values, but in the meantime, we want to avoid the potential outliers, right? We want to minimize the impact of the outliers because we are using the field collected data. And as you can see, one of these V2V applications, intersection movement assist, showed increase, like statistically significant increase in TTC values. Right? Basically, based on the definition of TTC, the higher the TTC, the safer the vehicle interaction, basically. Right. So here we have statistically significant increase, which is a good news for us. And also for lane change warning and forward collision warning, we saw a marginally insignificant results. They are also increased in TTC, but the estimated p-values, they are a little bit more than 0.05. And for EEBL and BSW, we have inconclusive results because we have insignificant TTC change based on the experimental design. Okay, so these are the results for using the field collected BSM data. So now let's look at results for the crash-based analysis. But before we look at the actual results, so we actually encounter some challenges when we are doing the crash-based analysis. So the main challenge is that the crash records, which are published by the New York City Police Department, NYPD, they cannot be linked to the instrumented vehicles due to the privacy and liability concern. So the result of that is that crashes involving all the vehicles in NYC during the study horizon were used for the crash analysis. So considering that there are a lot of safety-related confounding factors that occurred, at the same time with the New York City CV project, which include the COVID-19 pandemic recovery process and the Vision Zero project, planned special event, and so on. So basically, the crash analysis results should be interpreted as a combined treatment effect for all the potential safety-related treatments, including, one of them is, the New York City Connected Vehicle Pilot. Okay, so here we look at 2 types of crashes, which are the rear end crashes and the side swipe crashes. So for the rear end crashes, they are specifically for the forward collision warning and emergency electric brake light, because these 2 V2V applications, they specifically target the rear end crashes, right? So during the study period, there are 4,581 rear end crashes in the city. And we estimate the CMFs, the crash motivating factors, for the injury crashes and also the property damage only crashes. So there are no fatal crashes during the study period. As you can see, the estimated CMFs, they are less than 1, which means that there's a safety improvement, there's a reduction in the number of crashes. But for the injury crashes, we have a marginally insignificant results. And for PDO crashes, we have a statistically significant results. And for side swipe crashes, which are specifically for the blind spot warning and lane change warning, right? Because these two V2V applications, they are designed to reduce the side swipe crashes. So during the study period in the NYPD database, we have 1,471 crashes, and we separated into the injury and fatal crashes and the PDO crashes. As you can see, for the injury and fatal crashes, we do not have the statistically significant results for the estimated CMFs. And for the PDO crashes, we have a less than 1 CMF estimation value and also statistically significant results, right? So basically, we can see there are reduction in PDO side swipe crashes, and also the reduction, in PDO rear end crashes during the study period. And also specifically, it is very important to account for the exposure of crashes. So generally, generally speaking, in safety, we often use traffic volume. So in this case, it is very difficult to collect the traffic volume data for the entire city at any given time. So what we did is that we use a sort of a surrogate surrogate crash exposure. That is the traffic volume data collected at bridges and tunnels provided by MTA. And we use that as the surrogate crash exposure to account for the potential COVID-19 recovery effect. Okay, so now let's look at some conclusions and lessons learned. So basically, based on the analysis of the AISD field data, out of 9 evaluated applications, we have 5 of them show statistically significant safety improvement. 2 of them show marginally insignificant safety improvement. 2 of them show insignificant safety improvement if we use the 0.05 as a significance level. And conditioning on addressing the privacy concern of the participant and stakeholders, I mean, one of the potential lessons learned is that we may consider use a different procedure to preserve the location and temporal information in the future as much as possible, so that we can conduct more detailed research about the impact of spatial temporal factors on safety performance. And also, more factors may be considered in the design phase to increase the low quantity of some of the CV applications. And like I mentioned, several of the CV applications do not receive enough events. So for example, one of which is the vehicle turning right in front of bus. So basically from January to September last year, there's only 1 recorded event for that application. So basically in the future, we may consider some factors including transit bus participation and pre-deployment driver behavior analysis and so on. And again, this is in today's webinar, I listed some of the key findings and elements of this the safety performance evaluation aspect of the NYC CV project. If you want to know more about it, please feel free to check out this report right here. And also, we have a future webinar dedicated to lessons learned and future research. So with that, let me just quickly go over the future webinars here. So we have a webinar dedicated for pedestrian applications, like I mentioned in the beginning, and also a webinar dedicated to simulation-based safety evaluation for connected vehicles, and also a lessons learned and future research deployment roundtable discussion. So stay tuned for future webinars. And these are the references in this slide. And with that, I'm gonna stop right here. Thank you for your attention. And these are our contact informations. So feel free to reach out to us if you have any questions. And I'm also happy to take any questions right now. Thank you.
Thank you very much, Dee, for that great webinar. Thanks everyone for attending and watching. So now is the Q&A portion of the webinar. So please use either the Q&A box at the bottom of the screen to enter your question, and I can read them out loud. If you want to ask your question out loud or say anything, please hit the raise hand button and I'll call on you and allow you to unmute at that time. So if we have one question that has just come in, so I'll start with that one. Dee, the question says, my question is, do the drivers follow the warnings, and have you checked the performance of the application?
Right. Yes. Thank you for this question. So basically, as you can see, as I presented, we basically evaluate the driver's response behavior for each of these safety applications. And then we basically extracted several driver behavior response so that we can have a relatively comprehensive analysis of the driver response to the CV warnings. As you can see, like I summarized here, basically out of the 9 evaluated safety applications, we have 5 to 7 applications that show statistical significance, driver behavior change, or marginally insignificant driver behavior change, right? So basically, we can observe the driver behavior change due to the CV warnings. And also, in terms of the performance of the applications, like I mentioned, there is actually webinar for to demonstrate the operational capabilities of all the applications. I'm sorry if you guys cannot hear the video sounds, but feel free to check out this webinar right here. All the videos are published there, so you can see how each CV applications operate. And also during the data cleaning and processing phase, we actually tried our best to see the performance of the applications from a data perspective, and then we have tried to identify the potential erroneous or illogical observations and try to repair or clean or remove all those scenarios before doing the analysis. I hope that answers your question. Thank you.
Yeah, thanks. And for a follow-up to that, I'm just going to provide a link in the chat to our webpage on this project and the output. So the webinars and reports and everything else is available at that link. It's in the chat box. So Dee, there was one more follow-up portion of that question, which was how are the data stored and uploaded?
Oh, right. So yeah, I mean, in terms of the data storage and uploading, I mean, please feel free to check out the first report right here. It includes all the details related to how the data are collected from the vehicles and how the data are collected from the infrastructure and how the data are stored, obfuscated, and uploaded to the data ITS data sandbox.
Okay, yeah, and then Dr. Jenny Gao has also put a message in the chat in response to the previous question about the reaction percentage and performance. So check that out in the chat. Thanks, Dee. Moving on, we have a question about the curve speed warnings and asking why they appear to be pretty low. And I think there's a reference to slide 27.
Right. So yeah, this is a good question. So basically, right. So basically, if you look at, let me see, speed curve speed right here, right. So I mean, yeah, this
is the number of data events. Sorry, not this slide.
No, yeah, of course, yeah. So this is the number of events after curve speed compliance. So basically, during the data collection procedure, we found that there are false positive curve speed compliance warnings at that location. So basically, that location is actually a curve connecting local streets to the urban freeway, right? So that is, I mean, some of the events, some of the warnings are being given to the vehicles moving on the freeway. So that is why after the data cleaning, there are not many of the events left. I hope that answers your question. And also feel free to check out the data published on the USDOT Data Hub sandbox so that you can have a more better understanding about that. Thank you.
Okay. And the next question is, what's the difference between your before-after analysis and the traditional DID analysis?
Right. So yeah, that's a great question. So basically, when we are deciding, what method that we want to use for this project, we actually consider several causal inference methods, one of which is the DID method, as you mentioned. But the thing is that because of the data obfuscation procedure, we do not know the exact location, and also we do not know the exact date of the event. So that puts some constraints about like the commonly used causal inference method that we can use, including, for example, time series intervention, including also the DID method. So basically here we employed a relatively more commonly used method, and also a relatively simple test to get the results. But again, I mean, like I said, if in the future CV testing, sort of a more sort of different data obfuscation procedure can be employed, then certainly all more causal inference method and more factors can be included in the data, basically in the data analysis and also in the performance evaluation procedure. Right. I hope that answers your question. Thank you.
All right, and I don't see any more questions in the chat, so if you all want to raise your hand and say anything, I'm happy to unmute you or type in any last questions.
Oh, yes.
Now's your chance. So while you're doing that, I am once again going to drop the link to our website on this project in the chat. And if you visit that link, you'll also be able to find the upcoming events Dee spoke about. So including the videos Dee mentioned that have more information, the reports that were generated by USDOT as a result of this pilot, largely written by the project team, more information, news, and finally the upcoming 3 events in this webinar series. So now is a chance I'll plug those. So on October 25th, we're going to have Dr. Jenny Gao present on the PEDSIG application Dee mentioned, but which was tested to help the suitability for people with visual disabilities to cross the streets as part of this project. On November 2nd, Dr. Khan Asbe will present on simulation-based evaluation framework for this project. And finally, we'll be concluding on November 9th with a roundtable discussing future directions for connected vehicle implementations throughout the country. So please join us for those 4 events. We'll send email events out, but also visit this website to learn more and sign up. As I mentioned at the start, this webinar will be uploaded to C2 Smart's YouTube channel, where you can find this and other events and previous recordings saved for you to watch. Other than that, any final words, Dee, you want to share with the audience?
No, I just want to say thank you. Basically, again, I'm presenting today, but this is a joint work from all of us and all the people that I mentioned at the beginning. Everybody contributed to this completion of this project.
And I saw a bunch of our colleagues from the New York City Pilot team, from DOT and TransCore, et cetera, joining us today. So thank you for your contributions to this project. Thank you, Dee. That was great presentations, and thank you everyone for attending.